Hi everyone, I'm Manas and I'll be hosting your discussion this week. We'll go through the concepts of neural nets in this discussion and later on we're going to look at how to implement Project 3. Here are the topics that we're going to be covering in the discussion. We'll start with why do we even need neural nets? We'll look at what are neural nets, then we'll see what is MLP, and we'll see the forward propagation and back propagation algorithm in MLP. And at last, we're just going to go through some of the PyTorch code. PyTorch is a popular deep learning framework. All right, so let's begin. So uh, let's start with what were the problems faced by perceptron? So perceptron has a property that it can compute anything that is computable. However, there are several things that are not computable. For example, in the case of XOR gate, given an input A and B, perceptron can't converge with any decision boundary. However, suppose we are able to give additional input to perceptron with the value of A dot B. Now the perceptron with these three input is able to converge. So giving an additional input is the whole idea behind neural network. So let's see what neural networks are. Right. So neural networks was modeled on basis of our own on our own brain. So it basically learns by making mistakes and correcting them, just like human beings. We have several kinds of layer in neural networks, so like input layer, hidden layer, and output layer. We also have activation functions in between. Activation functions role is to bring non-linearity in neural nets. Otherwise, the effect of adding 100 hidden layer will be same as the effect of adding one hidden layer. Some of the common activation functions are sigmoid, tannus, relu, etc. You'll be using some of them in your project. All right, now let's see what is MLP. So MLP is a special kind of neural network in which there is at least one hidden layer, and every node in a layer of the network is connected to every other node in the next layer of the network. Here you can see the architecture of MLP for regression as well as classifying tasks. For regression, we just have a single output, which is our final value. For the case of classification task, our output layer has same number of nodes as number of classes in our model, as number of output classes. At the end of the values generated, we generally take a softmax of these values, which changes these values into probability, and we end up selecting the value with the higher probability. So we make everything zero except the one which had highest probability. So in the image of 2, you're likely to find 1 here because 0, 1, 2. All right, let's move on. Let's see forward propagation in MLP. So during forward propagation, the data moves from left to right hand side. We start with input layer, calculate the output here, 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 and then calculate output at the final output layer. Every edge here in the figure is a weight, which is like multiplied with the input of that particular neuron. Finding the weighted sum for this neuron will give, and adding a bias term at end will give us the input of this neuron, which is like forward propagated later here, here, after multiplying with this weight, and so on. And similarly, you at then get output as well. Forward propagation is a non-linear linear operation due to the activation functions that are present. Like in this case, f is your activation function, which gives the output y. All right. Let's see the back propagation step now. So during back propagation, errors are flown from right side to the left side, with errors at output is just generally target minus the predicted value, or yeah, target minus predicted values. With the errors calculated for every neurons, the weight are also updated with the help of the learning rule, here as shown in the equation. The errors at at arbitrary node, sorry, the errors at arbitrary node J depends on all the errors generated by the errors at node J depends on all the nodes to which it is connected, and it's given by this formula. Now, it might seem a bit complex formula, but what it's basically saying is the error at this node is error on all the nodes that is connected to, that is this, multiplied with their corresponding weight. And at the end, we multiplied with the input of this node. So intuitively, it's just like if node J, suppose this node has a big weight on this node, and if this node's error is, if this node has a big weight here, and there's a big error here, then even the error of this node will be large. So that's what this formula is doing at the end. All right, so this was the backpropagation step. Unlike forward propagation, this step is in fact a linear operation because there is no activation function involved. It's just a derivative of an activation function, which is linear. All right. Let's look at some of our code. First, we're going to look at some basics of PyTorch and like how you can use PyTorch for MNIST classification. For your project, you do not need PyTorch, but the code that's provided to you mimics the structure of a PyTorch code. And it's a pretty good, like it's a highly used framework, so learning PyTorch is a good thing. Let's look at the code. So our task here is to classify the images of black and white images of digits based and predict what digits those are. So initially we just load the necessary libraries. We select the device. Like if you have GPU, your processing would be faster. Otherwise, this is a simple code. It will even work on a CPU. So if you get a CPU here, that means it didn't find a GPU available. Here are some hyperparameters that we are testing. So we are running it for 4 epochs. The batch size for training is 64. Batch size for testing is 1000. We have a learning rate as 0.001. And for every 100th step, we are going to log our accuracy. So the first thing is to load the dataset. So we load it using this torch vision dataset, which MNIST is just like bunch of images. So we download it and we apply this transformation. What this transformation does is it converts, first of all, the images into a tensor. Tensor is basically an array. And then it normalizes each tensor with the mean of this and standard deviation of this. Yep. We do the same thing and load the test dataset as well. And since we normalize the training, we have to normalize the test as well. All right. So let us see what our dataset looks like. So it has, okay. So our test dataset is loaded in batches of 1000 and, and each is of size 28 cross 28. Okay. Let's plot and see on what are these. So you can see these are digits and the ground truth values are given as well. And now let's just train it. So we import some other things as well. We import some functional components that are like our activation functions. We import optimizers as well. Optimizer is nothing but it's just going to update the weights. So this is our neural network class, which is inherited from nn.module. So this is from PyTorch, nn. So we need to make this inheritance in order to make our own neural net class. And the structure of our neural network is we have our input layer of size 784 because we had like 28 cross 28 as input. Then we have a first hidden layer of size 32. So fully connected 784 cross 32 weights. And then dot linear is a fully connected network. And then we have a second hidden layer, and then we connect this to a output layer of size 10. So we have a second linear layer of input size 32 and output size 10. So this is gonna give us like 784 input, 32 hidden layers, 30 hidden layer of size 32, and output layer of size 10. For PyTorch, we need to define our forward method as well. And it all, for us, it computes the gradients and everything. So we don't need to worry about it. We just need to initialize all the layers and give a forward method. Forward is just forward propagation. So first thing we do is we change this 28 cross 28 array into 1 cross 784 array. Then we input this into first fully connected layer and pass to ReLU function. And then we pass it through the second fully connected layer. And at the end, we apply the softmax layer. So this is our whole forward function. Now, let's make an object for this class. And we're going to move the object to GPU as well. We need to select an optimizer on like how are we going to update weights. There are various optimizer available in PyTorch. Some of them are like Atom, AtomW, stochastic gradient descent. You can use any one of them and just pass your model's weights. So network.parameter gives you your model's weights. Okay, so let's see the training loop. So we put network to train mode. So in the training mode, your weights are actually updated. If you are just doing a evaluation or testing, you need to put your network in an evaluation mode. So the gradients won't be calculated in that case. So we go through our batch, we move our data and targets to GPUs as well. We clear out all the gradients we had till now, and we do a forward pass, right? And then we just calculate our loss, which in this case, since it's a classifying task, it's a cross entropy loss. And now we need to do a backpropagation after forward pass and calculating loss. So for that, we just do loss.backward. And after backpropagation, we need to update weight for every weight in the network. So for that, we just use optimizer.step. And for the log interval variable, we for every log interval, we print all these things like train epoch, loss, and accuracy as well. And optionally, if you want to save the parameters, you can save it as well. I've just written it. Let's see what our testing loop is like. It's almost same as training, but here we just like put network on an evaluation mode and move everything out into GPU. And here in this case, we just do a forward pass to get output, and we just check on like what was our accuracy and print it as well. So let's see. Let's just first print accuracy without training, and then train it for the number of epochs. That was our hyperparameter, and then test it again. So test it after each epoch. So initially you can see our accuracy was just 7% before training. And then you can just see just after one epoch, it reached 93% because the data set is pretty easy. And similarly, after 4 epoch, we reached 95% accuracy. We can also see the output on these images that we displayed above, and we see like most of them are correctly predicted. This was fairly easy to train just because data set was so easy. All right. Okay, let's move forward with your project 3 and see what is being asked there. So yeah, I'll just make this look a bit better so we have it easier to follow. All right. All right. So here we are doing our own in project 3 adversarial attacks. Let's go through the code and understand what's given to us. So here we are just importing some files. Some helper functions are already given to us that we're going to need: softmax, cross entropy loss, and the relu activation function. The our class is also given to us. Most of it is already there. So there's just some of the functions that you need to um, finish by yourself. Initially, what we do is we load all the weights of the trained model that are already given to you. Let's just see the similarities like in forward propagation. So even the code of forward propagation is given to you, but let's just see. So from the slides, you can see like uh, Zi is calculated with like um, h of I minus 1 and plus bi. Here also, if you see, it's a similar thing. Plus bi, and this thing is your h of I minus 1, as h of I is just ReLU of zi. So h of I is just ReLU of zi. Most of the things are already given, and I think you need to fill, first of all, the gradient method. Now, how to calculate gradient is also given to you in the writer. If you have a look at, yep. So dl by dx is your gradient, which at the end just simplifies to this expression. And every term is already given to you. How do you calculate it? So like dl upon dz4 is just p minus y. dz4 by dh3, this term is just wi transpose, which is in this case is w4 transpose. Similarly, you can calculate every one of these things, and at the end, your gradient would be just a multiplication of every one of those terms. So self dot gradient would be this into this into this into this, like all of these products. And that's how you can complete your gradient function. All right. Let's come back to attack later. But okay, for the fast gradient sign method attack, even the code for that is given, like how will you going to implement it. The basic idea is your X, the data, you shift the data based on the sign of your cross entropy loss. So basically, you need to calculate your cross entropy loss with the prediction and Y. And suppose X was your input. So you calculate the sign of this thing and you just return X plus this into some constant that you have already set. For this particular case, the constant epsilon is 0.1. And to set the constant, we have provided a method called set attack budget. All right. Yep. One thing is, you need to be like this exactly won't run. You need to make sure the dimensions match and everything. As prediction here will just return you a scalar value, but cross entropy asks you prediction to be an array. So if you just blindly copy this is not going to work. So just make sure, like I've just provided like a template code on what you need to do. And let's see, how do you run it? So you load your data and your parameters of model. You create the classifier and you load the params for that particular classifier. Okay, they have just displayed the image. Okay, this is fine. So your basic idea is You set your attack budget, which in this case is like 0.1, and then you iterate through your test set. And so your x comma y is your input and your true output. Your new x, that means after doing adversarial attack on this x, you can get the value of new x from clf.attack, which you are going to implement. This is going to give you a new x. And based on this new x, you will ask model to predict what is my new y. Now, if after applying this, the value of your new y changes, like new y is different from your actual y, that means your adversarial attack was successful. However, if it remains the same, then that means the attack was not successful at all. So this is like one way to do adversarial attack. And this is how you can, from here, you can calculate your accuracy and whatever is required. Similarly, if you want, you can, like here, this was like fast gradient sign method. You can, I think you need to create your own method as well for the later part of for the project, but it should be fairly simple, and just see what methods work, what doesn't work, and just get the explanation. Yeah, I think that is it for this discussion. If you have any doubt, uh, feel free to post on Piazza or visit any of our officers. Okay, thank you.